Hello everyone. Uh, Today we are going to talk about the run-to-run variability on Theta and the best practices that we have as of today for performance benchmarking. First, to introduce the problem that we are discussing today, uh, for an application, the metric is how much time it takes on a supercomputer, right? Like if it takes t amount of time, is that t is varying from each run to run of the application. So for example, here, if you repeat an application, if it's taking like 300 seconds one time, 220 or 370 seconds. So from each run to run, the time it takes varies. So the equal work is not equal time. This is the problem of run-to-run variability. And the sources of run-to-run variability uh, uh, on Theta, the system that is in focus of our discussion today, uh, what we identified were like at the core level, what are the different sources of variability? Then at the node level, and then at the system level, the interconnect level, what are the different sources of variability? This work was a collaboration between the Intel and the performance engineering team at ALCF. So we went about identifying all the different sources of variability at each component level. As I said, starting from the core level, node level, and then the whole system level. And these sources of variability are, some of these are very well known in the literature. For example, the operating system noise effects, how that is affecting the application runtime, and the frequency scaling effects. So the latest architectures, most of them have this DVFS, dynamic voltage frequency scaling. How does that impact the time for taken for an application? And the manufacturing variability. So when you're talking about this multiple cores, are there any sources of variability caused at the fabric manufacturing level itself? And then the node level, when you have multi-cores, whether the core to core, whether there is any contention between the shared cache accesses, and are there any effects? So these latest architectures have multiple memories like high bandwidth and the traditional memory DDR, whether that is causing any source of variability. And then at the network level, the network congestion, the topologies, the latest kind of topologies, whether that is whether that is leading to any source of variability. So in a systematic way, we went about identifying the different sources of variability and characterized how much each is contributing to the real applications and what are the mitigations wherever possible. Some of the sources, as I'm going to talk about, are not mitigatable. In that case, what are the suggestions that we have as of today to do performance benchmarking? Okay, these are the different sources of variability. What are the challenges? As you can see, it's not desirable to have run-to-run variability. So this leads to unreliable performance measures. And if you do any performance tuning, if you have a matrix multiplication code and if you do some tuning like loop tiling, and if there is in the presence of this variability, you can't ideally attribute what's the quantum of improvement that is coming out of this performance tuning, whether the improvement that you're seeing is due to the code tuning or is because that the variability, the congestion effects are not there in that run, and that's causing the improvement in performance. So it's difficult to characterize the performance tuning effects in the presence of variability. And from the job scheduling point of view, even from the user perspective, if the time taken for an application is changing from run to run, for the job command, you can't give like exactly how much time it takes. And also from the system utilization point of view, it complicates the job scheduling. So the system in consideration today is the Theta. So first I'm going to talk about the Theta architecture briefly, and then the systematic procedure that we have taken to identify the sources of variability and suggest the mitigations wherever possible, and also point out what is unmitigatable sources of variability and what are the best practices we have for the best performance benchmarking. So Theta system is a Cray XC40 system. It's the top 21 in the recent top 500 list. And there are 15 similar systems in the top 500 supercomputers. The point why I'm mentioning this is what we're going to discuss today is relevant for other supercomputing systems as well. Theta has like 4,300 nodes. All these nodes are like the peak performance is 11.69. And these nodes are Intel Xeon Phi, the Knight's Landing architecture. There are different variants of Knight's Landing, but what we have on Theta is 7230, which has the clock frequency of 1.3 base frequency and the AVX frequency, the SIMD vectorization frequency is in the range of 1.1 gigahertz. And there are 64 cores on a KNL and 2 cores, and this is a tile-based architecture, and 2 cores share the same L2 cache. And at the node level, each of the node and KNL has 2 types of memory. The traditional DDR memory that's of size 192 GB, and the high bandwidth memory that's called the MCD RAM, multi-channel DRAM, that's of 16 GB in size. I'll discuss later about the cache mode and flat mode, how the MCD RAM could be operated. And the network on Theta is a Cray Aries interconnect. The topology, that's how the nodes are laid out, is the Dragonfly network topology. And the routing that is used in these kind of Dragonfly systems is adaptive routing instead of the static routing that's used in BGQ kind of architectures. So the different sources of variability that we examined are at the core level, whether the operating system is causing any noise, and whether there is any difference from the manufacturing point of view, core to core variability. And 2 cores are sharing the same L2 cache, whether that is causing any source of variability, whether any core is preferred in the shared L2 cache access. And at the node level, whether the MCD RAM, the memory mode, whether that is causing any effects to the variability. And the well-studied topic is the congestion at the network level, network congestion, and how much is the contribution of the network congestion on Theta to the application performance. And for these 3 different categories, we used micro benchmarks, mini apps, and applications as appropriate to investigate the sources and the quantum of the variability that's seen. So first, to start with the core level variability. So as I said earlier, equal time, equal work should take equal time. So in this case, KNL has 64 cores, and we are running a to see how whether from the core to core whether there is any source of variability. We ran the same serial dgem. It's a matrix multiplication code. So the idea of picking matrix multiplication is that we made sure that the working set for that the matrix is small enough to fit in the L1 cache, so that there are no other sources of variability other than operating system. So we ran the same serial dgem benchmark that fits in the L1 cache on all the 64 cores, and the expectation is that all the 64 cores should behave the same way, and all of them should take the same amount of time. The y-axis here is the time. So as you can see, on core 0 and core 1, the time taken is higher than the rest of the cores. And when you compare the max to min, that's one of the metrics that we are going to use throughout this presentation. So the difference between the maximum and the minimum time, that variability is around 11% difference. So something is contributing to this variability, and the expectation is that the operating system, because all the 64 cores are running the same benchmark, but the operating system services, the daemons, should also run on this one of the cores. And by default, the operating system runs on core 0. So the Cray, the operating system that runs on the Theta nodes, has a feature called core specialization. It's in Cray operating system feature, allowing users to reserve cores for handling operating system services. So when you run the same experiment with using this core specialization feature, the variability is reduced to 5%, and instead of the maximum time taken on core 0, now the time taken on core 64 is the core 63 takes more time. What this core specialization does is that the operating system services will run on one hyperthread on the last core, the core 63. That way, the main hyperthreads on cores won't get affected by the operating system noise. So I want to also mention that each core on Theta, the KNL, has capability of 4 hyperthreads. So that feature is utilized here to optimize the operating system noise. So the recommendation is to use core specialization where you're running these kind of small benchmarks where the core to core could impact the performance. To dig a little more deeper into this core level variability and what's the quantum of variability that you can see with the operating system noise, there is a standard benchmark called like selfish benchmark. All it does is within a tight loop, it has a timer, and it just increments the timer in each iteration. So there is nothing, so start and stop, and there is nothing in between, and that is run multiple times, and the time is recorded in each iteration. The expectation is that since there is nothing between the start and stop, all should take close to kind of minimum time here, where majority of the blue dots are here. But as you can see, in some iterations, the time reported is in the order of 200 microseconds. This is where the operating system, the core is taken by the operating system, and so the start and stop time is recorded is in the order of 200 microseconds. So all these events are noise events, and this graph also shows that what's the time quantum for the operating system noise is in the order of 200 microseconds. So, and with using core specialization, those noise events are rectified, and this benchmark is run on a single core. So when you use core specialization, the benchmark is run on core 0, whereas with the core specialization, operating system services are run on the last core. So there are no noise events. Core specialization is an effective mitigation for the core level variability. And to further point out the effects of the variability, you should be aware that the effects of the variability due to operating system noise are kind of meaningful to look at only when you are running the benchmark, micro benchmarks, so which takes in the order of like a few seconds or smaller than that. So the graph, the plot here is showing the benchmark time here in the order of less than 1 second. So each of this green line shows the iteration for one benchmark iteration. And when you have such a benchmark, and if a noise event occurs during one of the iteration, and then when you compute the max to min time between the iterations, the noise event contributes to the variability. Whereas when you have a benchmark that takes a little longer time, in order of like 5 seconds, the noise events are distributed evenly, and in that case you won't see the impact of the noise events, and you notice that okay, there is no variability. So the time scale matters here. So as I said, if you're looking at very minuscule time scales for the application, that's when the variability due to the core specialization helps. Nevertheless, it's always useful to use this, especially for if you're running MPA small latency benchmarks. You must use the core specialization. Feel free to interrupt if you have any questions at this point. Switching on to the other topic of the node level variability. The KNL, as I said earlier, has two types of memory: the DRAM, the traditional DDR type of memory. Sorry.
So here we have two questions.
Yeah.
Ben has asked, what is the OS doing with its preamps of a DGEM? Is it just a timer interrupt to enter the schedule, or are there other things? And then Shingfu asks, what is the core specialization? Is it similar to core binding?
Okay, so for the first, let me take the second question. The core specialization is a Cray operating system specific feature. So if you're familiar with how you run jobs on Theta, with AP run, you say minus R1. When you specify minus R1, you're reserving, like if you say minus R1, what it means is that you're reserving one hyperthread on a core for the operating system services. So what internally the operating system does is, what we have the knowledge is like speculation that it runs on the last hyperthread on the 63rd core, and it somehow distributes the load of the operating system across all the cores. And to the first question on whether the timer interrupt, yeah. So the resources, the core is shared between the operating system activity and the application activity. So that's time shared. Let me proceed. At the node level variability, KNL has two types of memory: the DDR, as I said, and the MCD RAM. And MCD RAM is the high bandwidth memory, is of like size 16 GB and 480 GB per second effective bandwidth. So as you can see, the bandwidth difference, there is a huge difference in bandwidth between the high bandwidth memory and the DDR. So it's desirable to use the high bandwidth memory wherever the working set fits in with the high bandwidth memory. So to facilitate the use of the high bandwidth memory, there are two different modes that are available. One is the flat mode, and the other one is the cache mode. Sorry, Tim, can you close that? Yeah. Sorry. So MCD RAM can be operated in two modes: the flat mode and the cache mode. In the flat mode, the MCD RAM is treated as a separately addressable memory. So MCD RAM is there and the DDR is there. And in the cache mode is, you can think of somewhat similar to how an L2 cache is to the L3 cache. So the MCD RAM is to the DDR. So with the advantage with cache mode is that user oblivious to how the user uses. So the advantages of the MCD RAM could be accomplished. But whereas with the flat mode, user specifically has to say that which portions of the application working set should fit, should be placed in the MCD RAM. So the sources of variability, what we identified were with the cache mode. And the cache, as you know, similar to how the traditional cache, the mapping between in the cache mode, the mapping between the MCD RAM pages and the DDR pages is direct mapped. And if you kind of recall how the traditional direct mapped caches, L1 and L2 cache, have the issues with the cache conflicts, the similar issue of the page conflicts happen with the direct mapped operation of the MCD RAM in the cache mode. So
here,
yeah,
sorry to interrupt. We have another question.
sure.
Murad asks, is there any disadvantage of using core specialization? If not, could it be set as a default? So he's asking if we should just use the core specialization as a default, or is not a good idea.
I think so. I at least use core specialization as a default, but I use it minus R1, so I just reserve just one hyperthread. But the feature, the facility, you can reserve minus R2 or minus R4. So if you say minus R4, what it means is that 4 hyperthreads are reserved for operating system activity. So effectively, you are losing 4 hyperthreads from your for your application. So depending upon your how you want to scale the code, whether to 63 cores or 64 cores on the KNL, accordingly you can use the core specialization.
Thank you. We have another question. Shangfu asks, for flat mode, what is the default case? Is DDR or MCD RAM?
Okay, so with the flat mode, you have to, the default means if you don't use anything in the flat mode, the data is picked up from the DDR. But if you want to use the MCD RAM in the flat mode, then you have to say like NUMA-CTL minus, using NUMA-CTL feature, you can avail. That's one way of operation, but there are other ways of using MCD RAM in the flat mode. So to answer the question, so if you want to use, so by default it is DDR, but if you want to use in the flat mode, you have to use the NUMA-CTL option.
Thank you. We have another question, and is Theta running zone sort, if I said it right?
Yes, so zone sort is run by default on Theta. That's correct. I'm going to attach that later. Yeah.
Thank you.
Okay. So the potential conflicts are with the direct mapped nature of the cache mode. So stream benchmark. So we use the stream benchmark to quantify whether there is any variability due to the cache mode. So the stream benchmark is used traditionally for characterizing the memory bandwidth. So it's specifically we use that stream triad as shown here, a vector A equal to bi plus a scalar times another vector. And I'm running the stream benchmark using 63 cores. So just to isolate any sources of variability from the core level, I just reserved one core entirely for the operating system. I'm running 63 cores with one core with a working set size of 7.5 GB. So that fits within the MCD RAM of size, like MCD RAM size is 16 GB. When run in the flat mode, the x-axis here is the different experiments, different jobs. With each job, there is no difference in the stream bandwidth that's seen, so less than 1% variability. And as expected, you won't notice any variation in MCD RAM read count or write count. Whereas when you run the same experiment with MCD RAM operated as the cache mode, you do see this variability. The first point is that the effective bandwidth, the maximum effective bandwidth that you see is much lower than what's seen in the flat mode. In the flat mode, we saw 480 GB, but whereas in the cache mode, we are seeing around 350. And here this what's highlighted here, and there are some runs which are taking 180 or 170 GB per second. Some jobs. So you can see that there are 2x job-to-job variability with using this the stream benchmark in the cache mode. So this, as I said, is occurring due to the MCDRAM misses. So the higher time corresponds to the lower write count and lower misses, and the lower time corresponds to high. Okay, sorry, we have so.
So here we have another question. So they ask if these jobs are all on the same node.
These jobs are not on the same node. Yeah, these are not on the same node.
Okay.
But okay. Wait. But if you see, it has each job. We also have an error bar. So we do repeat the experiment on the same node multiple times. So that variability within the node, within a job, that's is there somewhat, but not that as much as from node to node. Yeah, sorry, go ahead.
Okay, so another question is, what is the overhead for core specialization? Why do you use one core for it?
Oh, okay. Why I'm using complete core? So in this case, I'm using complete one core just to be sure that I want to hear that the motive here is to isolate clearly that the only source of variability. The operating mode that we have used is that make sure that only just one source of variability is there, so that we are attributing to the right point. I mean, I don't see any difference even if you run with 64 cores. We do see this same kind of characteristics.
Okay. So we have two more questions. So they ask if they could have a different page table state on different nodes at the start of each job.
Yes. So why we are seeing this difference is that these jobs that are run, so the previous jobs, how the memory footprint of the previous jobs, where the MCDRAM memory footprint the previous jobs left with, if you're operating from that's why we are seeing the page tables. The footprint is different across all the jobs. So in some different supercomputing centers, they do kind of reboot the nodes just to be sure that all have the kind of same memory footprint. But that's too costly to reboot the nodes with each job.
Okay, so another question: if you use the -CC option along with the -R for the AT-run to pin application to a specific CPUs, how do we know which cores to avoid due to the core specialization feature?
So with the core specialization, you won't kind of bind to which core the operating system activity runs on. That's done internally by the operating system. What we kind of heard from means I don't think it's any quoted, but what we heard is that it's run on the last core. So, but they may be distributing across the multiple cores.
Okay. And another question is, when you're leaving one core for the OS and using core specialization, do you ask for 4 hyperthreads? For example, all of the hardware threads available on one core, or only one hyperthread? And they said it doesn't matter which one they choose.
So it's only one hyperthread is used. That's the kind of that's the 4th hyperthread. So the last hyperthread. So if you can count, if you rank them as 0, 1, 2, 3, the last hyperthread is what is used for the core specialization.
Okay. And another question is, when you're leaving one core for the OS and using core specialization, do you ask for 4 hyperthreads? For example, all of the hardware threads available on one core, or only one hyperthread? And they said it doesn't matter which one they choose.
So
Okay.
Let me, in the interest of, let me go on and let me stop after finish the node level variability for a other question, if that's fine.
Yes.
Okay.
Thank
Thanks.
you.
So here the load time corresponds to higher miss count and higher write count. And okay, so this is the characterization with MCRAM. So the suggestion is to, so as someone pointed out, the zone sort does help reduce this variability that we are seeing in the cache mode, but that does not completely resolve the issue. So the zone sort, as in other supercomputing centers and even on Theta, zone sort is run, but that's not a clear mitigation. But as you can see from the architecture level itself, right, the direct map nature is causing to this variability. One potential mitigation is to reboot the nodes, but as you can see, to reconfigure the nodes takes huge amount of time. From the job, the system utilization point of view, that's not the ideal scenario. So but I want to point out the stream is on one extreme case which is highly memory bandwidth intensive. And if your application kernel is memory bandwidth intensive, and if you can avoid using cache mode, you can use the flat mode. That's the recommendation. But just to be aware that if you do want to use cache mode, be aware of this cache mode variability issues. Okay, moving on. At the network level, the network on Theta is Cray XC interconnect, the NIC and the switches, and how they are laid out is in the Dragonfly topology. More specifically, it's a 2D Dragonfly topology. So each group, so you can see each blue dot here is one electric groups in the Dragonfly terminology, and all these groups are connected in an all-to-all fashion. And when you zoom out one group, that's connected as a 2D flattened butterfly. So all the rows are connected all to all, and all the columns are connected all to all. And each router has 4 nodes connected to it, and these are called as many of you know, the features of these Dragonfly topologies are like low diameter topologies, but they do have, and the cost wise is also compared to like 3D Torus. Cost wise is also optimal, but they do have this issue of high chances for interjob contention. And there are several papers and in the literature talking about this interjob contention and the variability that's induced due to this. And so essentially, when you're running a job, how the other jobs which are sharing the same interconnect, how they are affecting the performance of your job is what the interjob contention that we're talking about. And that is, we can't quantify that very precisely, but it depends upon the size of the job, the node placement, the workload characteristics, whether it is communication intensive, and the co-located jobs that are running when you are running the job. That's not in your control, right? So to start with, we use the MPA Collectives, the all reduce 64, running 64 on all the 64 processes with 8 MB message size. And this is repeated 100 times within a job. And this experiment is run on several days so that we have the diverse mix of node placement and other co-located job mix. And we also ran one experiment in an isolated system run, means just after the maintenance when no other job is running. And in that scenario, when you repeat this benchmark multiple times, we do not see, as expected, no variability less than 1%. But when you run in the production mode, so the x-axis here is showing the different jobs, so potentially different job placements, different co-located job mix, and the y-axis is showing the variability, and each box plot is showing within that job how the variability is there between the runs. When you run like 100 times, how it is varying. So the message that so you can see it from the max domain, the variability is like 35% for this benchmark, and but you can't. And this, the best observed is running in the isolated mode. This is something you need to be aware of when you're running on any kind of, not just on Theta, but on any kind of Dragonfly kind of topology. In fact, any related topologies. So maybe one thing that we can learn from this plot is that even with the same node placement, there is high variability. So it's not that just the node placement is not the issue. Also, how the other jobs are impacting this job. So let me summarize what we have till now. So the core-to-core variability is due to the operating system noise, and if you don't use a feature like core specialization, core 0 could be slower compared to the rest of the cores, and this could be critical for micro benchmarks or even with MPA kind of low latency 8-byte all reduce or 8-byte broadcast kind of benchmarking. So, but when you have longer time scales, these the operating system effects is not noticeable, are there, but not discernible clearly. The core specialization is at the expense of using one hardware thread for the operating system. You can avoid that. And the frequency scaling effects, which we did explore but haven't touched on, are negligible on KNL because the frequency range is between 1.1 and 1.3, not much compared to some other Xeon cores which have much higher DVFS range. So we do not worry about the frequency scaling effects on Theta. And the node level variability, so with the memory bandwidth intensive benchmarks or codes, for example, like Neckbone or mini apps, have this issue of the MCDRAM page conflict issues, and when you're running in the cache mode, you can see significant variability. So the zone sort is there, the Cray Linux zone sort algorithm, but that does not help completely avoiding this issue. So the mitigation is run in the flat mode wherever possible. And the network level variability we saw with the collectives, there is this variability, and there is no clear obvious mitigation for this level of variability. So what we have seen so far was with the applications, with the different benchmarks, micro and mini apps. And okay, Neckbone is also a mini app, but it represents the NEC 5000 application. And it has 3 different types of kernels, like streaming kernels, which are bandwidth bound, and DAX-P kernels, and the matrix multiplication, the MXM, which is a compute bound, and there are communication bound like GSOP and different types of communication operations. So when you run in the flat mode, the total time is shown, and the constituent portions of the compute, communication, and memory bandwidth codes don't see any variability from the job to job 3.5x variability, which is reasonable. But whereas when you run in the cache mode, the same experiment, we do see this variability, and as expected, the variability in the run total time is correlated with the variability in the streaming kernel, which is memory bandwidth. So the cache mode is the page conflict effects are contributing to this variability. I mean, at least be aware that which kind of computer communication or the memory bandwidth kernels are affected by which source of variability, whether it is operating system noise or the cache mode effects or the network congestion. That's the idea of this slide. And for the Neckbone with a different input, it's communication intensive, and with a job to job, you can see running on 128 nodes, you see around like 32% variability from the max to min. If you just, if you remove that one outlier, it's somewhat reasonable, but just be aware that these outlier situations are possible. And maybe if this may answer one of the questions that was asked, we did study whether to find that ideal configuration with the node placement. So here in this case, I'm repeating the experiments on 256 nodes, the Neckbone. So each box plot there showing that repeating the experiments with the same node allocation multiple times. So there is high variability in this case, even with the same node placement from run to run within the job, there is variability. So potentially, some of the runs are affected by the other other jobs, the interjob contention. So possibly the node placement is we did try with the even the compact placement, but that's not the ideal mitigation to have like compact placement. That would it's not that would resolve the variability. Then with the milk application, milk is a lattice QCD applications. There's a kind of it's a point-to-point communication intensive. Yeah.
I'm sorry for interruption, but there are two questions. One asks, what is the parameters that you use for the Neckbone analysis? What was the problem size and how many iterations? And another one asks, what was the reason for the outlier that you observed?
Sure. Okay, so if you want more information from all these experiments, so I would point you to one link that I provide. I will provide at the one of my last slide. We had a paper at supercomputing last year, and as part of that, we also have an appendix for the reproducibility. So we do have the exact application benchmarks and the inputs that we have. So you'll feel free to use those to reproduce. Yeah, the outlier, as I said, in this case is that's what we are discussing earlier due to the congestion, the interconnect congestion effects. So in this case, the Neckbone is the communication intensive. The communication intensive kernels, the GSOP, and those kernels are affected by in this run, this outlier case, are affected by the other jobs. So because other jobs are sharing the same interconnect, that is leading to this higher times for these communication intensive kernels. So the interjob contention is a source of this variability. Okay. With the milk, it's sorry. So with the job to job, in the milk case, so just to have a reference point, it's around like 50% of the application time is communication intensive. So the communication intensive kernel takes 50% of the total time, and when you run that on like 128 nodes on Theta, it takes like you can see 74% variability at this point. I also want to point out that this is not something specific to Theta. Let me not reveal the names, but on the other systems we do have similar systems. We do have the users or even talking to them report more than 2x variability for this milk application. So I'm not saying this is a good, but at least this is not something new or specific to Theta. And running on 256 nodes, we see this 41% variability. Just to be sure that coming from the only from the network. Let me also point out that all these experiments that I talked about from the network level variability all are run in the flat mode using the MCD-RAM numCTL minus P option with the preferred option. So it uses MCD-RAM, but not in the cache mode, but it's in the flat mode. So we do, with using the Cray pad, we do see that the communication intensive kernels are the one which are affected by this. Okay, so as I said in one of my earlier slide, this is an issue. This kind of variability is an issue when you want to do some performance tuning. So in this case, we have a Neckbone, and so as I pointed out earlier, Neckbone has this small matrix multiplication kernels, and the Intel has a libxx as some library which has an optimized small matrix multiplication optimized for the KNL. And when we use that library for optimizing the matrix multiplication, we expect to see some performance improvement in the Neckbone performance. But in the presence of variability, when you run in the cache mode, so the blue violin plot here is what showing in the default case, and the green is what the optimized case. So there is this variability because the experiment is run in the cache mode. So when you just take these two, let's say when a user runs this experiment and the time taken is here in the range of like 730 seconds, and he changes the tuning, the libxsm, and repeats the experiment, the changed code. Let's say the runtime is in the 7-10 seconds. So okay, with just the two runs, the user, the application developer notices that okay, with the libxsm, you see an improvement of just 2%. But the actual scenario is that, and whereas in the extreme case, if the user in the first run, if he sees the runtime in the default case is 820 seconds, and in the optimized run, if he sees around like 600 seconds, he notices, oh, with the libxsm, I notice 35%. But the reality is different. With each run, it's the improvement is between like 2% and 35%. Okay, in the presence of variability, this is an issue with the performance tuning. So especially the impact that you're seeing with the variability, if in the range of like 10%, and the improvement that you're seeing with the tuning is also in similar range or higher than the what's variability seen, then it's difficult to attribute the tuning impacts. So one recommendation that we suggest is to repeat the experiments. But again, the question is how many times to repeat. There are some standards. That's where we have to start using the statistical metrics, like with the confidence interval. We can say that on an average with this tuning, the improvement is 18.8% with 95% confidence interval. So you have to repeat multiple times and see whether the confidence interval is higher enough to believe the results that you have. And similarly with the milk, also you notice this is a different scenario where the default case. So notice here the y-axis here is the flops. So the higher the better. So the default case is the blue violin plot, and the optimized case is the green violin plot. So these two violin boxes are overlapping. So could happen that by this tuning, the rank reorder tuning, so the milk, as I said, is a point-to-point communication intensive, and you can, when you're running 64 processes, 64 MPA ranks per KNL processor with a milk, you can do this rank reorder optimization to have optimize the communication so that much of the communication stays within the node. With that optimization, we do expect to see some performance improvement, but in this case, these two curves are overlapping. So if a user tries just two experiments, it you could see that with the performance tuning, negative impact on the performance. So because of this variability issue, you should be aware of that. You need to repeat the experiments and also start using this kind of statistical procedures to report the performance benchmarking, and be aware of especially when you want to experiment the tuning effects, be aware of these scenarios. Okay, to conclude, so we kind of used a systematic procedure to characterize the variability. So when you're dealing with one source of variability, we try to not have any other source of variability. So the core level variability, one mitigation is the core specialization, and see that the memory mode, and there are no other kind of source of variability like frequency scaling or manufacturing variability are not noticeable on kernels. And the memory mode, the cache mode page conflict effects. So if you have memory bandwidth bound kernels, try to run in flat mode, or just be aware of the variability that is potentially possible with the cache mode effects. And then network level variability, unfortunately, we don't have a clear mitigation. I mean, you have to understand that that's the kind of design decision with the topology of the Dragonfly, which looks into have a global system congestion optimization, and also note that the cost optimization of the Dragonfly, but the artifact of that is this the network congestion effects and the variability. So we have seen on the kind of real applications we do see this variability, and be aware of these, and we don't have the kind of clear mitigation for the network level variability. For more information, feel free to refer the paper that talks about these. And if you're interested in knowing more about the recommended statistical practices, refer this paper from Toast-Hofler at Supercomputing 2012. He goes into detail about the use of the confidence intervals and how to report, how to compare especially when you want to compare these kind of, you want to compare the results on a theta and some other similar system. What are the recommended practices to use are detailed there.